Hi, my name is Rozenblum, and I will be talking about an experiment protocol developed by Professor David Steinberg and myself as part of my thesis in applied statistics at Tel Aviv University. So, from which height can you drop your smartphone without breaking it? And while you're thinking about that, I'll ask you, how many smartphones will you be willing to give up for that experiment? This is exactly a sensitivity experiment, which play an important part of quality testing. They used to validate manufacturer statements and set thresholds for safe use of products. So the objective of such an experiment is to determine at which height you can drop your phone and almost never break it. Now, keep in mind that in statistics, we can't say never, so we want to say to have the phone break at a very small probability. And our solution is a good design of experiment. So a few ground rules for such an experiment. So we cannot re-drop a smartphone. So once we dropped one smartphone, we cannot reuse it. So that's why the sample sizes must be kept very small, because it leads to high costs. The phone can either be broken or not broken, nothing in between. And we have some prior knowledge about the phone sensitivity. So we know that from 10 centimeters high, it will probably not break, and from 100 meters high, it will most likely will break. And last, the higher we drop, the greater that the probability that the phone will break. That is just intuitive physics. So as I said, the probability that the phone breaks is directly linked to the height it's being dropped from. So how would you design such an experiment? The intuition is to have something like an up and down. So you have an initial height, and then if the phone breaks, you decrease the next height you drop the phone by some constant d units. And if the phone doesn't break, then you increase the height until you observe some broken phones. And this is what a standard up and down sample looks like. This time we simulated an initial height of 16 meters. And you can see that the 16 meters did not break. So we elevated the next height to 17.2. Our step size was 0.2 meters. And you can see each observation, what was the height, what was the outcome as the experiment moves forward. So one thing that you can see here is that initially it took about 4 observations to reach the actual median of the sensitivity curve. At 20 meters high, the phone breaks at 0.5 probability. And our initial guess was 16. It took the experiment about 4 observations to get there, to observe the first broken phone. That is wasteful. Another thing that's not really good about this method is that if you take a look around 24th observation, you see a height of just over 22 meters, and the phone did not break, which is something that we would expect at a very low probability. It took the experiment about the next 5 observations to adjust itself and get back to sampling around 20 meters, which is where we want to keep sampling. So the intuition behind our algorithm is looking at the sensitivity curve of the phone as a function of the stress. So we have a probability that the phone breaks as a function of the height it's being dropped from. And we have 2 parameters, one which is mu, which is for the location. Mu is the actual median of that sensitivity curve. At 20 meters high, the phone breaks at exactly half probability. And sigma is responsible for how skewed or dense the curve actually is. So we don't want to sample very high heights or very low heights, because it's not informative. We already know what outcome to expect. If we drop a phone from too high distance, it will most likely break. So we want to sample, we want to drop phones where we don't really know what's going to be the outcome, if it's going to break or not, which is about 0.5 probability. So our algorithm suggests choosing the next height to drop your smartphone at the height that minimizes the entropy of the response. So we have the response is either the phone breaking or not, and we calculate this entropy for each height in our range. And here we did so after 4 phones have been dropped, after 10 phones, 25, and 40. You can see that the biggest reduction in this entropy, which is a measure of information, or uncertainty, the biggest reduction is at the beginning, because every new observation gives me much more information than the 40th observation. So the biggest reduction is at the beginning. And you can see that our initial guess was about 16 meters. So that's where initially the algorithm wanted to drop the phones. And later on, as the experiment moved forward, it's shifted towards the area around 20 meters, which is the actual median size. So this is what a standard sample simulated by our algorithm. So we started at the same 16 meters high initial guess. The phone did not break. And then it took the algorithm only one observation to get to the area around 20 meters where it is actually expected to remain. Another thing that is good about this method is that it recovers quickly from surprising observation. You can see that it still has the up and down, and you can see around observation 24 and close to 30 and 35, we have a phone breaking where we expect it to not break. It did not affect where the next height to be chosen was, because it kept doing this up and down, which means that, and this is actually because this algorithm uses observation, the information from the entire sample rather than just the last one like the up and down methods. So regarding the estimation of our parameters, we do it completely Bayesian. So if we have 2 parameters, we have numerical sample. We sample a large n values from each one of their prior distribution. So we have large n pairs of mu and sigma. For each mu and sigma, every time we drop a phone, we have an outcome and a new height. We calculate the likelihood of these data. By normalizing these likelihood values, we get posterior weights. Now, the intuition behind this process is that if we have a sample pair of mu and sigma that is very close to the real unknown parameters, mu and sigma, their likelihood will be bigger, and their share of the weight in the posterior will also be bigger, which indicate that they are a better estimate. So here you can see our prior distribution that we gave for mu, which was, again, the 16 meters where we wanted to sample. And this prior is pretty wide. It offers a wide range of possible values for this mu. The actual mu in those simulations was 20 meters. And even after 44 observations, in purple, you can see the posterior distribution. So it became much more dense. And you can see that it offers a higher range than the initial 16 meters high guess. After 20 observations, we get a much denser distribution. And last, after the experiment was over, after 40 observations, we were much better being able to close in on the range around the true median, which is 20 meters. This is actually the quanti-posterior confidence interval for this mu parameter. So to conclude, we developed a method that uses our prior knowledge and reduces the uncertainty of the data in a fully sequential approach. Our estimation was entirely Bayesian, and we've managed to extract more information from the sample than the standard up and down method. Now, this research was developed for researchers at Rafael, which are used to work with the up and down methods. And the fact that our algorithm still keeps the up and down, yet extracts much greater information from this data is means that they would feel comfortable using this method and they can save their observations. Thank you so much.